this video, we show the practices that support ongoing changes in student thinking. The first of the practices is introducing ideas that students can use to reason with in the upcoming activity. This is an interactive form of direct instruction. The second is engaging students with an activity that generates observations or data. The second practice requires that students use the introduced ideas from the previous practice to reason with. The third practice is using this new knowledge to revise models and explanations for the anchoring event. This set of practices would be used 4 or 5 times throughout the middle of a unit to help students make cumulative sense of activities, investigations, and readings. One of my novice teachers and I share the task of introducing the idea of trophic levels and how energy is used by organisms to survive. She starts by prompting us to think about how living things use energy. I pick up a few minutes later by talking about phytoplankton's role in converting sunlight to energy that supports the trophic pyramid in the Antarctic.
We're going to start speaking the language of energy, and that's what she wants to introduce. And then when we do the activity, it's not a confirmatory activity. We're just going to use Molly's ideas as levers to help us make sense out of the activity.
Primary producers occupy the base level of a trophic diagram, as you can see. They convert light energy from the sun into chemical energy or food for other organisms. Before we dig deeper, I'd like you guys to turn and talk to the people at your table about why organisms eat other organisms. And I want you to remember your recent lesson on food energy. What sort of vital functions does food energy supply? In other words, why do organisms eat in order to survive?
Plankton, and it's a microscopic. The phytoplankton is not one kind of organism. It is a mix of all kinds of very small microscopic organisms. But a lot of the organisms that make up phytoplankton they have chlorophyll in them, just like land plants do. These phytoplankton are in the ocean. And so you might wonder, how do they supply food for krill? Well, there's a lot of phytoplankton. These microscopic organisms here are all pictures of phytoplankton. But I've got another odd picture in here, which is this one. It doesn't look like phytoplankton. What that is a picture taken from space. I'll show you a little blow up here. So this is the edge of New Zealand, taken last year on October 11th. On October 25th, the same satellite came by the same place and took that picture. That is, I'm not going to have you guess what it is, I'm just going to tell you. So this satellite is capturing billions of tons of phytoplankton because there was a bloom of phytoplankton. They started reproducing in enormous numbers. Plus there was some upwelling. Some phytoplankton are lower in the ocean and they well up to be more near the surface. But phytoplankton are so plentiful in parts of the world, you can see clouds of them in the ocean from space. So Kimmy is going to tell us why this activity is so important, and I'll tell you what the activity is.
Right. So last class we started looking into how different organisms in the Antarctic ecosystem interact with each other. So today we will be doing an activity that would help us understand better how energy is flowing from one trophic level to another trophic level in Antarctic ecosystem. And this activity involves cups and beans. So while you're doing this activity, I want you to think about what's representing energy and what is representing the organism. And also think about why the transfer of energy from one trophic level to another trophic level is in the shape of a pyramid.
What you're going to get, this is 1,000 beans. This represents 1,000 kilograms of phytoplankton. 1,000 kilograms. To give you a little picture of this, I weigh about 70 kilograms. This is 1,000 kilograms of phytoplankton. But what I'd like you to do is I'd like you to follow the directions. They are self-explanatory, but in the first part of the directions, you don't have to work with the beans. In the second part of the directions, the second part of our activity, what you're going to do is you are going to count these beans. You can lay them out on the table. You can lay them out in here if you want, but you're going to have to count them out and move them to a different trophic level. It's explained in the handout, but you will literally be taking beans out, counting them, and putting them in the next trophic level. And then you are going to figure out how many beans you have in this cup at that trophic level, which represent biomass. And then you are going to count out a certain number of beans that go into the next cup. I believe you're going to have 3 of these cups that you'll go through. Okay? So what I want you to do now is get together at your tables, and I want you to read through the first activity and get started on that. Scott and Graham are going to be the ones who move around and just there. Let me say one thing. When you split up into small group activity, we're not having Graham go around, for example, and check to see if you know what the instructions are. We may have to check on that, but our primary reason for visiting tables is to find out what you're talking about and what kind of intellectual work is going on, and to prompt you to think further. So when Graham and Scott come to your table, what they're going to do is they're not going to turn their back on the rest of the class. If they come to visit this table, Graham is not going to kneel down over there. He's going to kneel down over here and get at your head level so you can see the troublemakers over here. Who's not doing their work over here? People back there.
The star student.
The star student. So we're going to get down at head level. We're going to face the rest of the room. And we are not going to be parked here for 3 minutes. That's too long. About 90 seconds is what you get. Like 30 seconds of listening to what the kids are talking about, and maybe you just get up and go to another table without intervening because they're having a really great discussion.
Triple 3.
So if I could stop you for just 1 second. One part of this second column that I believe is important, and I'd like you guys to focus on a little bit, is translating this term, primary consumer, into your own language.
That's a good way to put it. I'm gonna steal it. Is that the same?
Is this?
That's final places. You're crow. I'm amazing.
Okay. So this is the final part.
Marie, can you say more about the sun?
Well, the plants only get a certain amount of sun and energy. You're staying in their space.
They don't get 100% of the energy that the sun is putting on them. They only get like a fraction of it.
So should we somehow represent the sun in whatever it is we draw eventually?
Yeah, we had thought that this was going to represent the sun, and so like I'd be phytoplankton and then krill and penguins, but this is phytoplankton and this is krill, so I think there needs to be like a way bigger jar of more beans.
You represent what?
The sun. The sun's energy.
The energy of the sun.
And the mash on the sun.
Come on, Graham, take over for me. Graham's gonna pick up for me. You gotta face the rest of the class. You get your back.
It's just Marcus in your
Marie
the,
was just
the
saying
sweet spot.
that she thought that maybe that should be the sun. And Greek also was collaborating with what you were saying about that being the sun. So, good idea. Let you take it from here.
So, I guess one thing I'd ask you to think about is if this we predetermine as a unit of 1,000 units, 1,000 beans, is it a good representation of the sun?
If it's like 1,000 to 100, maybe. It's like 10%, like everything else.
Is it like everything?
I don't know.
How efficient is the energy to transfer from?
It's probably like 1% or something.
Is it the energy that they're using for functions? For heat? Whatever? Or is it for their actual biomass?
So in your presentation, Molly, you were saying 10% that gets transferred to the next trophic level is strictly talking about biomass.
And energy. You said and energy, but I was confused because
maybe
Energy restricts the biomass.
is biomass.
Biomass is a form of energy, is what I would argue.
Yeah, it's true. It's chemical.
So what's the 90% that's left over?
It's
That
this. It's what the population itself needs to like, support itself.
So it would be like
Cell
thinking,
turnover.
well, cell turnover is a weird one because it technically is biomass, but you're losing it and then regaining it.
Yeah, that's a good question.
But you still have to eat stuff to keep that the net zero. Because if I stop eating, I'm gonna get smaller.
The important part is it's a net zero when it comes to an individual.
Yeah.
So maybe that energy is, that 90% is used for heat, sort of physical kinetic energy things that are displaced.
That's crazy, 90%.
I'm trying to say where does that energy that goes to produce biomass, the energy that doesn't produce biomass, where is that actually? And that's what he was asking. Because he was using biomass as you use energy to make biomass, I think.
So we're going to fast forward now, because I think that Scott and Graham had probably learned from doing their visits to each group, pressing them. I think in some cases you've asked them to pay attention to something they weren't paying attention to. What? A couple times. And then were some groups pretty on track, and then you asked a question that pressed their thinking further? Scott did?
He was doing it where he was asking us about what it represents, and this was good. Yeah. What do you mean by biomass and stuff?
Okay, that's an all-purpose question that you can ask. Whenever you do an activity, you're working with some representation of something else. So you can always ask kids, what does that represent that you have? In fact, if kids are struggling, that is one good question to ask whenever kids seem to be really struggling, is to back all of your heavier duty questions up to just what do you think a bean represents? And you can also note that after you would do this activity and write in the spaces that I've provided for you, that the last part of this activity is for you to redraw an energy pyramid in which I ask you to think about how wide should each of the levels be. And then what might you add as the labels on the energy pyramid as to what's going on at each level. Now, my triangle is too simplified. It doesn't reflect the actual math that you guys have calculated. So what would that pyramid look like? You could use graph paper to do this, count out 100 squares, 10, 1.
Oh, I just meant in the initial one, to not have it be super misleading, right in that triangle, right in 1,000,
Yeah.
100.
Yeah.
Even if it's spatially accurate.
Right.
At the end of class, one of my novices helps us complete the last of our 3 practices, which is creating a knowledge product that reflects what we now think we know about the activity and its relationship with our explanation for the anchoring event.
2, 1, 0. So we're going to make our summary table for our bean passing activity. So I want to know first, what kind of observations and patterns did you guys make? What did you see going on with the amount of beans as we went from cup to cup? Kimmy?
The amount of beans decreases as we go from cup to cup.
Okay. By how much does it decrease?
That's what I wanted to add on to Kimmy, is that only 10% of it was passed on.
All right. So only 10%. Were there any other observations you guys made during this activity? Seems like a pretty straightforward one. Only 10% of the beans were passed from cup to the next. So what does that mean for us? If we see in this representation that we're only passing 10% of the beans, what does that mean in the real world outside of passing beans in cups? Dennis?
I mean, 90% of the beans are left over, and they don't go into the next level.
And what do those beans represent? Those 90% that aren't passed on. Someone want to help Dennis out? What is that 90%?
That maybe a lot of that 90% goes into just maintaining the organism, or the
Right. So 90% of the energy goes to maintaining like Amanda said, the organism.
Okay, let me press the pause button and rewind.
Yeah.
So you said the word right?
Yeah, I did.
Yeah. So let's back up and pretend that that's a good response from Amanda, that it can be built on.
Okay.
Let's rewind it and say 90% of that energy goes to maintain the organism. So can somebody else add to what Amanda is saying about that?
All right, so 90% of the energy goes to maintaining the organism. Can someone add on to that? What more does that tell us? About maybe this 10%. Can you connect the, if 90% is going to maintaining, tell me more about the 10%. What does this mean about that? Graham?
10% is the part that goes into making biomass.
Do you want to add on to that?
Yeah, I agree. I think the 10% is representing the biomass that gets, or the energy that gets converted to biomass, and I think that we're concerned with that part because that's the part that can get passed on to the next stage too. It's the mass that can be, that's edible, right?
So what you're saying then is that the 10% that's being passed on is getting converted into new biomass?
It's edible by something else, yeah.
Okay. Did you want to add on to that, Zachary? Just so you had a hand up.
So I'm trying to figure it out. The 10% that's left over is what the next step up, the next trophic level up can use.
Yes.
Does any one of your classmates want to help Zachary puzzle through this?
Makes sense, but I think that we should be focusing on not on individuals, but on levels of the trophic pyramid.
Okay.
So otherwise, we're going to be focusing more on like how much do I grow, and if I have like a hamburger, am I more biomass? You're not biomass. Like you are in a sense, but what's biomass is like the level.
So you're trying to highlight the fact that we're not talking about just one krill and one phytoplankton at a time. We're talking about all of them as a whole.
Yeah.
Okay. So let's add that in with what we were saying about 10% building the biomass, like Scott was saying. And can you put those two ideas together into one phrase we could put up here for what this means?
At this point, I ask my novice teacher to focus the class on the third column of the summary table, which always asks us, how does this activity help us understand the anchoring phenomena?
Our question is, why is the Adelie population declining? That was our question. So how does this relate? The 10% we're being passed, and 90% maintains the organism. Taylor?
I'm just confused because I thought that they only ate 10% of it, so you get 10%.
So my question to you is, when you eat lunch, do you only eat 10% of it, or do you eat the whole lunch?
I eat the whole thing, so why didn't they eat the whole thing?
Why do we leave all the beans in the jar? Yep.
Does someone want to answer Zachary's question? Someone help Zachary out. Why are we leaving beans in the jar, Dennis?
It's because all those beans in the jar are what it takes to maintain the organism. It doesn't actually go into the biomass of the organism. So you have 1,000 kilograms of phytoplankton, and the krill have to eat 1,000 kilograms of phytoplankton, but then you only get 100 kilograms of krill because those 900 kilograms of phytoplankton went into the make the krill growing and maybe having some fun.
But I thought that matter didn't turn into energy.
We say this every day now.
Matter is energy.
Okay, we're gonna have to stop here.
There's the bell.